Okay, so in this video we will be talking about bootstrapping error accumulation reduction, or BEAR. And the motivation of BEAR is very easy. So the main motivation of BEAR is that the constraint that we actually imposed using BCQ is overly restrictive. So if you remember, in BCQ we are actually defined the ratio of the probability of taking an action in a certain state divided by the maximum probability of the maximizing action taking in the state to the both of the behavior policy must be larger than a certain threshold epsilon. And this defined somehow the set of admissible policies that we want to use in order to do our policy improvement step. And the problem is, like if you consider this problem, so this was the problem we were actually being addressing, is that we do not want to use these action values in here to do the backups in order to do the greedy policy improvement. We want to stay close to the distribution that our behavior policy induces into the data set. And what this distribution constraint actually imposed was that we want to have a set of admissible policies, and the set of admissible policies lies between an epsilon environment around the policy that we have in our data set. Meaning that at the end of the day, the distributions should be close to each other. So we are allowed to use some of the purple policies to actually represent our Q function. However, we might actually also want our distribution to take one of those distributions. So this is actually overly restrictive, and it might be a better way to represent the Q function at a certain state like this. And however, we cannot do that because the discrepancy between one of those orange distributions is too different from the behavior distribution. However, in the end, we just didn't want to select those ones, and both of them would actually result in the same, would actually have the same result. And if we would actually be able to select one of those distributions, this would be much easier, because then we would have a lower probability of actually selecting suboptimal actions around here, aside from the actually optimal action. And this is actually the main difference to BCQ. So BCQ actually tries to match the distributions of the policies within the state space. And in BEAR, we actually do not want to match the distributions. We just want to constrain both policies. We actually want to constrain the policy we are learning using offline RL to stay in the support of the behavior policy, meaning that the behavior policy or the data set that we have has a support for the values that we use to describe the distribution we use and the distribution that we learn. We will see in a minute how this actually works, but maybe look a little bit more closely why distribution matching is problematic, how BCQ is actually implementing it. So consider the one-dimensional grid world we have in here. We have a starting state, which is in the middle, and I mean, this could be arbitrarily long. And imagine that our agent starts at the starting state and is tasked to go to the goal state. On the left of the state space, no matter if you go left or right, you always receive a 0 reward. And if you are on the right side, you always receive a positive reward if you go to the right, and you can receive a negative reward if you go to the left. So you get rewarded if you come closer to the goal. Okay, and imagine that we have the following behavior policy that is generated, that is used to generate our data set. And it basically looks like this. So in any of the states that we have, going left is much more likely than going right. Left to S in here, there's a 100% chance of going left. So there's no chance of going right. And on the right side to S, there is a 90% chance to go to the left, and there's a 10% chance to go to the right. So on the right side, there is a probability of going to the right, but it is low. However, at this side, all of these actions actually are in distribution, and we have all of that actions and all of those states as part of our data set. And the problem is now, what is distribution matching doing here? And the problem with distribution matching is that we actually try to match the distribution of the policy we are learning to the distribution we actually see in the data set. And this will lead to the following problem, that we will always have a large probability of going left within that area, and the probability of really going right or like reaching the goal becomes negligible in its likelihood. And the problem is, why does it fail? And assume that we use the penalty that we use for distribution matching. So there was this epsilon parameter, and if this epsilon parameter is large, means that we are enforcing the action set to be very similar to the action set we have in the data set. And if we use a small epsilon, then we actually allow to actually back up actions that are not that likely in the data set. So if we have a low value, we have like Q-learning, we have a large value, we have like behavioral cloning. So a tight penalty somehow means a large epsilon. And the problem is that we are actually having overestimation in Q-learning, and the problem is that if the penalty is tight, so if we have a large penalty, there is the problem is that between S and G, the probability of our behavior policy is very large to go left. And the problem is that this low probability might lie below our threshold and be not within the admissible action set, meaning that if we have a tight penalty, so we want to stay close to the distribution of the behavior policy, we would actually lead to suboptimal behavior in here, and we would actually have only going left in our admissible state set. So meaning that in order to come up with a good solution in here, we would need a weak constraint. So we would actually need a low epsilon to actually also resort to the action selections we have only little times in our data set. So we need a weak constraint. However, if we apply this weak constraint, it might be the case that that we actually, if we have a weak constraint, this means that if we are left to S, we will always select the left action. And the problem might also be because we have a weak constraint and we don't have those actions in the state set, the problem is that we will have a suboptimal behavior also on the left side. And the problem is, if we have a weak constraint, this might lead to the fact that even starting from S, we might then go to the left side of the problem, because we are learning and we have an overestimation bias in Q-learning, and at state S, probably going left might also look more preferable, and if we do that, we will even go left if we are in S. So I guess it took some time to really understand this problem. I really recommend you going to this blog post to actually read into this example a little bit more. But the problem is that underlying in this problem in here is that we try to really match the distribution, and we try to match the distribution using our penalty or epsilon. And the problem is that depending on the state space and the data that we have in our data set, it's not good to first use the same epsilon all across and to match all the distributions. We need to be more flexible throughout our state space. And this is exactly what the support constraint is doing. So with the distribution constraint really tries to match the distribution so that we actually have our epsilon environment where we actually have the admissible set of policies or actions that we can select. And they should be like, not be similar, but they are bounded to be not that much off. However, what we actually want to have is, if we have an in-distribution action in our data set, so we have an estimate or we have an idea of how the Q value in that looks like, this is fine. We are in the support of the data, and this would actually allow the agent to also back up values or bootstrap values for this Q values that are actually part of the data set. So this is what we want. We do not want to match the distributions. We want to select all the actions for which we have a support through the data set that we're using. And if we are actually allowed to use a support constraint instead of a distribution matching constraint, this allows us actually to recover the optimal policy with a probability of 1, because we are actually, for all of these states, have a support of going right This allows us to bootstrap the optimal action, and this allows to recover the optimal policy of going straight right starting from S. Okay, we will go not that much in detail for Bear, but the idea is just to give you a little bit of an intuition how the difference between Bear and BCQ looks like, because they, from that perspective, are very similar. So this is the Q-learning objective that we have. We have the similar setting that we have the maximizing action A prime in S prime, which is our backup bootstrapping target, and we have the policy that is just the argmax over our action set in here. And in Bear, it is a little bit different. So we have a policy constraint. So we have an epsilon environment around our action set. So we have a restricted action set. And this the restricted action set contains actions that are within the support of the behavior policy. So remember, we did that also for BCQ, where we said, okay, the behavior policy, so the ratio of being selected, should be with respect to the action to probability of the action that maximizes pi beta at S should be larger than some threshold, meaning that it should be well represented with respect to the maximizing action, meaning that the distributions are close. And the difference to Bear is simply to say, okay, I include all the actions in my restricted action set where the probability of having this action being selected by my behavior policy is larger than the threshold, meaning that it is part of the data set, and we know that there is at least a non-zero probability of selecting this action using the behavior policy. Meaning, in this case, if you have an epsilon like this, and this is the distribution that defines the probability distribution of selecting action A and S, or this is the action and this is the distribution over S, and this would actually mean that the action set in our restricted action space would contain all the actions from in here, I guess it's something like -3, -3.5 until +3.5, because it is within, it is larger than a certain probability epsilon that the behavior policy is actually selecting this action. And then in here, it's the same as in BCQ. So the policy is just the argmax over the restricted action set. Okay, so the main difference is actually these terms, and how is then Bear actually different from BCQ so much. And the goal is actually or this was also the main problem that BCQ was addressing, that we want to get the maximum Q value of the restricted action set in a continuous action space. And the idea is also similar to what we have been seeing in the perturbation model in BCQ. The idea is actually to train an actor P psi that satisfies that the probability of A of S is larger than 0 if the probability of pi beta is larger than epsilon. So we train an actor that is actually outputting this action. So we can formulate something like an optimization problem like this. And this is something that is just for you to notice. I will not go into detail how this works, but it boils down to the distance matrix between those two policies, and the distance metric is basically implemented via the maximum mean discrepancy in here. That actually allows us to turn the policy improvement step into a constraint optimization problem, where we maximize the Q value such that the mean discrepancy between pi psi and pi beta is below some constraint over epsilon, which is exactly this one. So if we have a constraint of 0.05, we want every action to be a part of the action set, meaning that we want to maximize the Q function with the constraint that this actually holds. There is a lot of math involved, and how you can do that. If you want to understand it, you need to understand a little bit how maximum mean discrepancy is working. There's a little bit of a primer in here. However, I also recommend you in reading that. However, as you have seen, as you see it, it's only for reference, so this will not be part of the exam. The idea is just to estimate the maximum mean discrepancy, and if you are able to estimate it using a Gaussian kernel approximation in here, then you can actually constrain the optimization problem of maximizing the Q function. And there's a lot of magic happening also in here with dual gradient descent, things like that. But this is not part of the exam. If you're interested, go to the paper or here to this Medium article, and then you can actually read it up. However, so Baire is conceptually very similar or is building on top of the same ideas of BCQ. However, it uses a different distance function based on MMD to actually implement a support constraint instead of a distribution constraint. And this actually allows then Baire to also outperform BCQ in all of the environments. So you see in here, so this is Baire, so the orange line is Baire, and the blue line is BCQ. And you see that with Baire you are allowed to actually outperform BCQ because you are not overly restrictive in the policy improvement step. Yeah, so there's a lot more results, and exactly. There's also then coming now solutions where you see that I don't know where it's in here, so I guess there is where's the optimal and the random data. Now I see what's the okay, the optimal data is the bottom row and the random data is the top row, and you see that Baire is actually pretty good also in recovering good strategies if the data set that you are using to train is just random data. Okay, so if exploration in general is not a big of a deal, and you can actually use Baire to even learn a policy from random data. Okay, so important to know for you is that Baire and BCQ are conceptually similar, but BCQ implements a distribution matching strategy which is overly restrictive and that hinders the policy improvement step, and Baire just softens that, lessens this a little bit, and just restricts the policy improvement step to actions that are actually part of the support of the dataset of the behavior policy.